Now let's get back to the business at hand. Ax equal to b. Okay. Now our Ax equal to b that we have been dealing with comes from this equation. Stream function, Laplacian of the stream function is equal to the vorticity. This is what we wanted to solve right here. And we found that if you discretize this thing, it becomes a giant Ax equal to b problem. Okay? Now, so far, we have, 5 ways to solve this, right? That we've talked about. We've talked about you can just do Gaussian elimination. You can do LU decomposition. You can do Jacobi iteration, Gauss-Seidel iteration, generalized method of residuals, Bice-G step. So actually 6 ways. So we have 6 ways to solve this so far, that big Ax equal to b problem. So let's do number 7 today. So number 7 is the Fourier transform. Okay? Now, the Fourier transform is basically a way to represent data. If you want to think of that matrix as just data, in terms of frequency space. To transform, to put things in physical space into frequency components. Okay? That's what a Fourier transform effectively does. And the definition of the Fourier transform, let me write it down, then we'll start using it, is the following. The Fourier transform of some piece of data, or a signal, oftentimes we call it, is the following. You take some function, f of x, you multiply it by what's called a kernel, and you integrate. Now notice what I'm doing here is I have a function of x. I multiply it by this e to the negative ikx. That's the most important thing to think about here. And I integrate over all x values. And what it gives me is a function of just k alone. Okay? We'll talk about it in a minute. Now, that's to put it into k space. We'll talk about k space, which means our frequency space. To get it back, there's the inverse Fourier transform, which is the following. It's the opposite. You take this signal in the wave space or frequency space, and you multiply it by, again, e to the ikx. Now, notice there's a sign change here. That's minus. This is plus. By the way, the Fourier transform, depending upon which textbook you look at, can be defined in many different ways. Sometimes the minus is here, plus is here. Sometimes the minus is there, plus is there. Sometimes they don't do 1 over square root 2 pi. It's 1 over 2 pi here, or 1 over 2 pi there, and the other one doesn't get anything. So it's not unique. You just have to know, however, which one you're working with. Okay? So in particular, it's really important we know which one MATLAB works with. Okay? Because that's what we're going to be working with, so we have to stay consistent with that. Now, let's talk about e to the ikx. I'm not exactly sure when in your life you learned this. And I'm trying to figure out, like, I can't remember exactly when, but there was this Euler identity. Do you remember this? E to the ikx is just really cosines and sines in disguise. Okay. And what does k represent? K are your wave numbers. Or, really, they measure your frequency or your period, whatever you want to call it. That's a direct measurement of frequency content. Okay? So what are we trying to do here? So part of what we're saying is we're going to take a signal, multiply it by sines and cosines, as it were, all possible frequencies. Notice, when I do this, k is any value. And I'm going to integrate this thing up against these values and get out some function, which is now it's now a function of these frequencies. Okay? So what the Fourier transform, why it is so famous in some ways, is that Fourier in the early days of analysis said, look, you know what? I can take any function you give me, and I can, in fact, represent it as a sum of sines and cosines. Okay? So sort of it was kind of a revolutionary idea back then. It was like, come on, sines and cosines are just oscillatory things, and many functions are much more complicated than that. But he said, no, doesn't matter. What I'm going to do, though, is you give me a finite domain of the function. I can represent that on a finite domain. And because they're cosines and sines, you know they're periodic, right? So since they're periodic, really, you have periodic extension of these functions. Okay? And in fact, right away, as soon as you start working with this, whatever your domain you're going to do expansions on, you have to start thinking about periodic boundary conditions. Okay? There's your restriction. We'll talk about ways to get around this, potentially. All right, so this is what you're going to do in this Fourier transform. Now, to some extent, you could say, well, why would I take something and represent it in terms of sines and cosines, frequency, content? Because that seems a little bit, okay, so fine. It's just another way to represent anything. I mean, you can take any signal, and ultimately what this is going to result in is just a transformation. And there's infinite number of transformations you could perform on any signal. Why Fourier? Why is this one important?